Okay, sir.
Audible.
Okay, sir. Okay. Thank you. Yeah, very good evening to everyone. So, first of all, I would like to thank our guest speaker, Mr. Manoj Kumar Sabonayagam, for accepting our invitation to share his experience. And also, I welcome you for today's session, sir. I would like to welcome our respected all the faculty members and students for this wonderful session. It's a great pleasure for me to introduce our guest speaker. So, Mr. Manoj Kumar Sabonayam has completed his Masters in Aeronautical Engineering from MIT, Anna University, Chennai, and he has around 8 years of experience in stress analysis, and is currently is in a position of Senior Stress Analysis Engineer in Boeing India Private Limited. He is having a good knowledge in finite element modeling and analysis using Nastron, Patron, Abacus, and Hypermesh for metallic and composite structures. He also has an on-site experience in Chula Vista in USA for 3A350,000 program support, having a good experience in handling various types of FEA non-linear problems. And he also undergone various projects of around 3 to 4 projects. So one of the projects is Boeing India Private Limited under Structures Group. So the project was structural analysis of Boeing subcomponents, and the client was Airbus France. So role of the project was analysis engineer. So you also have various actions of UTC Aerospace Systems Private Limited, Aerostructures Group, and also he was worked in a project of structural analysis of A350,000 pylon truss reverser attachment structure using DFEM integration to GFEM technique. So he is also a project analysis engineer and analysis engineer for all this project coordination. So with this vast experience, we are going to have a wonderful session for today's year, and with this vast structure, and I would like to ask all the participants to interact with the guest speaker so that everyone can get a maximum knowledge of the session. So once again, I welcome you, sir, for this wonderful session, and I hand over the session to you for the floor to the students. Sir, you can take over the session, sir, and you can start your presentation.
Yeah, you're able to hear me?
Yes, sir, it's clear.
Okay. Actually, I'm just finding difficulty in just sharing the screen. Let me just know whether you are able to see the screen. You're able to see my screen? Hello?
Yes, sir.
Okay. The screen is visible?
It is visible, sir.
Okay. Thanks. Thanks everybody for inviting this lecture. I'm honored to be present over here. About here. So we will just start it. I think you people mostly all the mechanical engineering groups. So before just starting the session, I want to know how many people are just familiar with all these aircraft propulsion system or even any power plant. You people have gone through coursework and how you are be familiar with. Hello.
Manoj Kumar, sir, share your screen.
I'm sharing. You are able to see. You are not able to see.
Yeah, not share
Screen is
any
shared, but
screen.
not the slide.
Not visible, sir.
The PPT is not visible.
Once again, share.
Okay.
Yeah, now visible.
Now it's visible.
Visible, sir.
Now the
Okay.
slide is visible.
Thanks for confirmation. Yeah. Before going the session, just want to understand since you are just mechanical group and how much you are just familiar with power plant propulsion systems. How they just gone through all these coursework. So people are more familiar about these propulsion systems. Hello.
Yeah, audible, audible.
Yeah, I'm just asking, like, how much people are just familiar with all the propulsion systems and what are the power plant systems and how the energy being extracted and so is there any coursework being extensively studied in mechanical engineering group? So just want to get a brief idea about it so that I can explain more better actually. Hello.
Yeah, audible, audible. You can continue.
Uh, I'm just asking question like how much people are familiar with propulsion systems and all the whatever we are done, they have done in the coursework about the electrical systems and the power plant. Basically, the energy is derived.
So
Hello.
actually, we don't have that propulsion system as of now, but we are familiar with that power plants, all those things, various power plant operations and related to the power plants.
Okay, great. So yeah, that's what I want. Like, if you before starting with,
Yeah,
you should be having some idea about power plant, how the energy production has been happening, with respect to the uh, air suctions and all blades, so that you will have a basic idea of what is being explained over here. Okay, so
yeah,
okay,
yeah,
we
yes,
can
sir.
start.
Yeah,
Yeah,
yeah.
okay, we can start with this presentation. Okay, generally, what are the different types of an aircraft engines and the application? What we are going to see in this presentation is the types of aircraft engine and their application, and aircraft engines and efficiencies. What are the main driving factors for commercial aircraft design? And this and nacelle and thrust reverser. So you would have heard or not heard, I'm not sure. So nacelle is a kind of a cover or cowl to the engines. So that also contribute to the thrust. So that also we can see. And what are the different technologies and different programs, whatever the uh, flight programs we have. So those are all the main topics we are going to cover. So let's go to start with. So these are the types of aircraft. So also one more information, like once people have any clarifications, doubts over here, you can stop anytime and just ask to clarify. Okay. Okay. We'll start it. So generally there are two
Sir,
types
just a
of
minute, sir. Sir,
yeah.
sir, your voice is little buffered, sir.
Hello. You're able to hear now?
Yeah, sir, your voice is not audible clearly. Little buffer is there.
Now it's okay.
Yeah, okay, sir.
Okay. There are generally two types of aircrafts. What we see. It's not an aircraft. You can say it's a kind of a flying machines. So how it has been determined is based on the propulsion system. Okay, so one is a fixed wing. So one is a fixed wing system, and next one is a rotorcraft. So which is nothing but a fixed wing is nothing but your aircraft, and rotorcraft is nothing but your so named as helicopter. So basically, what are the basic difference here? Is, what exactly the design parameters comes into the fixed wing and the rotorcraft. So when you talk about a fixed wing of a flight systems, it may be a commercial flight or a military flights. So what are the basic difference in the propulsion system design is aspect ratio. So aspect ratio is your total aircraft to length wing to the breadth ratio, and sweep angle of sweep is the wing how much is going to have an inclination of the sweep. Then engines, so there will be a air breathing engines will be installed and the inlet. So these are the four basic design differences which we have to notice in the fixed wing concept that's in the flights. And when it comes to the rotorcraft, the basic design difference is on the tail rotor. So that's the basic difference between and also the rotors, whatever it's been rotating wing. Basically, it's a kind of a fixed wing and it's a kind of a rotating wing. So it's a basic difference between an aircraft and a rotorcraft or a helicopter. So going to the next slide. So how do these flights or aircrafts going to be flying? It's just an explanation over here. So basically, they have three forces, whatever we find, or so four forces. One is the lift, which is pointing upwards, and weight, which is coming down, and the drag and the thrust. So drag is the opponent to the thrust, so it will just reduce the thrust, try to reduce the thrust, and thrust motion is coming from the propulsion engines, which will make the flight to move forward in a forward motion. And lift is basically how much is going to have a maximum lift or the servicing on a specific height, and weight is the total weight which is going to contract the of the flight. So these are the basic four airplane forces which is going to drive your flight in motion. And basically, when you talk about a flight, they have three types of axes according to which the motion is being controlled, or 3 degrees of freedom, you can say. One is, as you see here, the pitch axis, which is rotating along the, you can say, via z direction, and a roll axis, which is along the axial direction, which is going to be rolling, and then yaw axis. Yaw axis is again it's along the downward direction. So according to these three motions, the flights have been uh, stabilized, and it is going to have a maneuvering effects. So when you come to the rotorcraft, so totally how the rotorcraft functions is a bit different from the airplane forces. Here, the rotary blades, whatever we have, it will create a suction force. So if you see here, there is a left hand side and right hand side wing. So there will be the left hand side wing, a rotary wing will try to suck up the air up, and the right hand side rotary wing will push the air down. So with which there is a forward motion of the rotorcraft. So that's how it been the motion is being forwarded. And and also when you go for a reverse motion, again it will be kind of a vice versa, where the left hand side rotor wing will have a upward suction force, and here it's a pushing down force, with which we have a reverse motion. And when you go for a additional thrust to move inside, there will be a tail rotor which is being placed at the end of the flight helicopter, so which will guide the motion towards a forward accordingly to the clockwise or anti-clockwise motion. So this is a basic difference how a flight motion's been happening. So these explanations given just because you people are new for the aerospace industry, and you can have a good idea about how the motion of a flight is going to happen. So this is how the motion is happening. Let me go to the next slide. So okay, so now you see this flight particularly. This is a Boeing V-22 Osprey flight. So can you just uh, see or the difference? What is the difference we find here in the flight system based on the previous slide? So you can have a suggestion on this actually. Hello.
Yeah, tell me.
Yeah, any comments on this flight? Like, how do you interpret this flight? Hello.
Yeah, I think no idea about the specific.
Okay, it
Can you
has
explain?
both. It has both fixed wing, and at the end there is a rotor also. So it is a kind of like a hybrid form, uh, which has collaboration of the fixed wing, which has and also the rotor, the rotating wing as well as the fixed wing. So it is a combination of both. So what's its application and advantages is like it has the maneuvering effects in a different forms. So it can be going to a vertical flight condition. Also, like it can go with respect to the performance of the flight, and performance of the rotorcraft. So it will have both the combination of advantages. So it's a combination of helicopter, rotorcraft, as well as fixed wing. So that's the basic application over here, and it is used for the military types or the defense types of the types. So going to the next slide. There are what are the different types of engines? I think you might be studied these things, basic things. Turbojet, turbofan, and turboprop. So what are the differences there? Is turbojet is the flight engine which has uh, the higher thrust with high nozzle velocity, which just pushes the air with the high thrust, which it will have a very high velocity of the flight. And generally, this turbojet has been used in your defense aircrafts or military aircrafts. And when it comes to turbofan, okay, before that we can go to turboprop and then turboprop. Turboprop is kind of like medium velocity flights, and it has higher performance but lower thrust. So it will not have a very high speed of the aircraft, but it will have a higher performance and it will be sustaining in the air for so long with respect to the because of the propeller fan at the front. So that's on the turboprop. When it comes to turbofan, instead of a propeller, there'll be a fan over there. So basically, what exactly this represents is we have the thrust in both the motion. One is the using the thrust due to the nozzle exit, as well as a thrust due to the mass flow rate. So there'll be a bypass airflow over here, which will be mixing with the final exit with the thrust air which is coming inside, which will add up uh, the thrust vector, which will have a better optimization between performance as well as the velocity of the aircraft. So it's an added advantage with respect to both turbojet and turboprop. Has the turbofan. So most of the commercial flights or all the commercial flights uses this particular type of engine, which is called turbofan. So coming to next is a turbo shaft. So what is turbo shaft is nothing but what we see in rotorcrafts. So the rotorcrafts, the air engines just pushes here, and there'll be a kind of a compressor turbine, and the exhaust will be coming over here. And there's a shaft over that which will drive the motor. So that's basically the principal mechanism of the turbo shaft. And finally, the ramjet. Ramjet is kind of like whenever we have very uh, high thrust or high velocity flights, which is going for with a Mach number equal to 1, which doesn't have any of the compressor blades or anything. It just directly the fuel will be injected to get the high flammability, and we will just have a CD nozzle over here, convergent divergent, which will push the air with a very high speed. And this basically used for kind of like very supersonic flights. It is used in the defense aircraft. So these are the basic types of engines what we see in our aircraft industry. So coming to the next slide, so this is a G90-115B, the most powerful and largest engine, and it is used on 777X flight. So what exactly it has, or the types of components which is holding this engine, is you have a turbofan and a compressor blades, and basically it has a combustor uh, turbine blades. So I think you might be knowing the mechanism. A compressor blade will squeeze the air. After that, that air, compressed air, will be going into the combustor where the air fuel injection and the combustion is going to happen, and it drives the turbine blades. And further, the turbine blades will have a high velocity, which will drive again the compressor blades with dash shaft, and partially, and the partial of the other air is going to push to the nozzle, and from the nozzle we will just have a convergent portion which will increase the thrust vector, and this is one type of propulsion injection is going to happen. And apart from that, there is a uh, bypass air which is going to flow over here. It will directly mix over that thrust which is going to have the air, and we will have more, with which we can have a more thrust with lesser drag. So this basic principle of this is basically a turbofan engine actually. What we are showing here is a very powerful engine till now what we are using in our flights actually. So these are the some basic equation which you have just gone through your coursework, which is nothing but m dot p, which is nothing but your mass flow rate, and inlet velocity minus exit velocity, plus the pressure difference into the area. I think this basic propulsion device, how it is working, I think that's a basic equation. Coming to the next slide, so there is a, what is the major advantage between turbofan versus turbojet? So turbojet, how we are just going to have a increase the thrust is through the compressor, combustor and turbine, and after that we will have an afterburner, which is kind of additional thrust to increase the thrust. So basically the fuel injection is happening in combustor. Again, a fuel injection is being injected over the after the turbine blade, which will even more increase the uh, thrust of the, or the velocity of the air which is passing from the nozzle. So to have a extra thrust, we will have a afterburner device over here actually, which is the process with same of what is happening in the combustor, which is fuel air injection. So bypass air flow, as I said before, there is a kind of a core air passing over here, and bypass air will be flowing, and both will be mixing at the nozzles end condition, which will have enough thrust. So this is how there's a kind of a basic difference between a turbojet and turbofan. So this has a bypass flow, but this doesn't have a bypass flow. But to have an increased air velocity, we will have an afterburner device coming after the turbine blades. So that's a basic difference. So generally they have three spools. So what are the spools? So two spool and three spool engines. So basically, if you see the shaft connecting between the turbine blades and the compressor blades. So when you have a compressor blades and there is a turbine blades, these two are connected with the shaft. So when you have a intermediate stages, so low pressure compressor, intermediate pressure compressors, high pressure compressors, and a combustor and a high pressure turbine, intermediate pressure turbine and low pressure turbine. So how it is being connected is one shaft. Spool means it's nothing but a shaft. So one shaft or a spool is connected between each of the stage actually. LP compressor to the LP turbines, and IP compressor to the intermediate pressure turbine, and a high pressure compressor to the high pressure turbine. So these three spools will adjust the velocity between the blades with the high rotating speed. Accordingly, we will have a higher efficiency in our thrust. So when you increase the stages of these uh, blades with respect to the compressor blades and the turbine blades, we will have a higher efficiency. It will have an advantage of higher efficiency of the thrust to come in. So that's a basic uh, idea behind to add more spools and shafts. When it comes to the two spool, it has only two shafts. That is, it has only low pressure compressors and high pressure compressor, which is connected to low pressure turbine and high pressure turbine. So only two shafts is connected. So three spool engine concept has higher efficiency compared to the two spool. This is a later on discovered by the RR Rolls-Royce engine aircraft manufacturing company. So this is a proprietary of Rolls-Royce, what they are using in their big engine section. So to give us some idea about the uh, engine companies, the two main, the largest engine companies are GE and Rolls-Royce. So GE and Rolls-Royce holding the largest engines manufacturing companies, and there are a lot of small engine manufacturing companies like Pratt and Whitney and even Snecma is there. So those are small engine configuration. But when it comes to the high big engines configuration, they have been dealt with only GE and Rolls-Royce. They have the whole overall market in their aerospace industry. So this is about the spools how it is going to derive the design in our turbofan engines actually. So coming to this, so this is a kind of like how the evolution of the engine takes place. So when it started with the first flight, the first commercial flight by the Boeing 707, that's the first commercial flight in the market. So if you see at the time, it started with a thrust of 17,000 pounds. So that's the starting time when they designed the engine, and the evolution took place. And this is the bypass ratio beta, which is approximately 1 something, and the evolution take place. And after so much of years of evolution at the 2011, with so much of optimized and increased technologies, increased design efficiencies, so they are able to achieve some around 74,000 pounds of thrust. So that's the increase in thrust, how much they have achieved the span of time with from 1958 to 2011. And you see the aspect ratio, sorry, that bypass flow is almost equivalent to 11. So it's kind of like great because of new technologies, because of new inventions, this kind of evolution has happened. Okay, coming to the next slide. So now if you see here, this is a GE CF56 flight for a Boeing 737. The thrust is approximately 30,000 pounds, and you see the ratio for this flight. And it started with this is a Pratt engine for F-22. This is a commercial flight, which is around 30,000 pounds. So it has what are the design parameters it is demanding? Demand high efficiency, fly at low speed, 6.9 engine has large inlet area, so it has very large inlet area. Engine has low specific thrust, and the inlet to output is approximately equal to 1, and it has very high propulsion efficiency. So this on the commercial flight, how they are just achieved. And if you go to the same like defense aircraft, what are the expectations for a fighter aircraft? So they demand high thrust to weight ratio. Here they will demand high efficiency, whereas here the thrust to weight ratio, and it should have a high speed, and the engine should have small inlet area. But here they should have a large inlet area because it's based on the performance. So here it is based on the how much is the speed of the flight we need to achieve. So the requirement varies with respect to the commercial and the flight aircraft. So according to the requirements, the design, the overall the uh, blades and the overall the design and the components and the complete configuration is going to totally change between the commercial and the fighter flights. And you see the engine has very high specific thrust, whereas here low specific thrust. And should have a very high exit velocity to the outward velocity, and should have lower propulsion efficiency. So these are the basic requirements between the difference on the requirements between the commercial flight and the fighter flights. And of course, if you see the thrust here, it is almost 35,000 pounds, and we have 30,000 pounds. So coming to the what are the major components in the design parameters for the engines is one is inlet. So what is the inlet over here is the the streamline. The inlet is a starting portion of this one engine, which is streamline the airflow and streamline the airflow. So continuously draw the air in the engine. So it should diffuse to the compressor. So the air is diffused under the inlet portion, and then the second stage is compressor or the fan. So in the fan will just the squeezed airflow will be just compressed with respect to the turbofan, and then the compressor blades. So this basically a compression zone where the compressor is going to happen. Then finally the next is the combustor where the actual ignition is going to happen. The combustion process is going to happen where the energy is converted from chemical to thermal energy, and relatively the constant pressure is maintained over here. And then finally the next stage is the turbine blades, There are 2 or 3 turbines in series. There are a lot of turbine blade series out there. So the purpose of the turbine blades are basically two purpose. One is it will drive the compressor blade, and second thing is uh, it will just also it will just increase the velocity of the air which is driving after the turbine blades. And then finally the nozzle. The nozzle will function of the nozzle is to increase the momentum of the air, which raises the velocity of the existing mass flow. So these are the basic stages how an engine is going to work. So basically, it's a air breathing engine, and the same principle is applicable for the even the power plant product, what you see in our energy production, whatever it is being derived. The difference is the difference is like there is a kind of a turbine blade over here, but that compressor and the turbine blade configuration is a little bit different from it. But overall, the requirement in the design is almost the same with the aircraft and the power plant. So even this turbofan is also whatever we see the flight engines is also one kind of power plant what we have. So coming to the engine efficiencies, so how do you just calculate efficiencies? These are all the basic equations which we just gone through. Uh, Nothing but thrust and outlet velocity by the mass flow rate into the pipe. So basically the thermal efficiency and the propulsion efficiency is going to have calculated total velocity, and finally it derives to 2 by 1 plus the exit velocity by the outlet velocity. So these are also basic equations. I think this all the propulsion books will be showing these kind of equations which you can calculate the efficiency of the propulsion. So, so this is the basic graph between propulsion efficiency versus the force by mass flow rate. Uh, that's basic information. So how it is going to vary, and so future what we are going to have achieve is future is headed for ultra high bypass ratio engines with a very small cone. So what is the future is we should have more bypass layers, which will increase the more thrust, uh, ultra bypass. So that's design is going to be coming in the future generation actually. Okay, this is how the efficiencies of the engine type system. You see the as speed increases, the propulsion efficiency of the turbojet is lower. But when it comes to the turboprop, once the velocity increases, it drops out. But if you go to the high bypass turbofan and low bypass turbofan, it's intermediate. So it will satisfy both turbojet and turboprop. So it will have a gradual increase while increasing airspeed. So this is the basic difference and how the efficiency is being playing around with respect to each type of engines. Okay, these are some of the engines in the aircraft where it is being used. And also the bypass ratio is being given. Rolls-Royce Snecma, which is used in the Concorde, and Snecma is used in the Duffield aircraft, and Pratt& Whitney. So Pratt& Whitney is also they manufacture small engines actually, and it has been used in F-16, F-15, which is fighter flights, and General Electric F404 is also used in a lot of the fighter aircraft, and Eurojet and Climo. These are the small companies, engine companies, which also manufacturing the engines have been used actually, and Rolls-Royce Trent 900, which is the largest engine, and G90. So these two are competitors actually. They used in big aircraft like A380, 777, which is kind of a double decker, which has passenger capacity of almost 2,000 people at one shot. And Rolls-Royce 10,000 is used in the 787. And accordingly, the bypass ratio has been distributed where it has been exactly used. So this kind of like evolution has been used. So it's a airliners demand like to which engine to be fit. So airliners customers will have the option to choose their engines. Actually. Accordingly, they will be choosing which engines they require based on the efficiency and based on the fuel consumption, specific fuel consumption. So that option is being given to the airliners, and they pick up the engine requirement which they require. So coming to the specific fuel burn. So ultimately, everybody's requirement is fuel is the largest component of operating costs in airlines are now turning to various fuel saving measures. So how they just save the fuels? So they basically have a new technology come upon with by pattern with means GTF. GTF means gear turbofan. So what is gear turbofan? Is the compressor blades and the turbine blades speed is operated with a gear. So gear mechanism which is being fitted over there. So the gear will be adjusting the velocity of the rotating speed of the compressor blades and turbine blades, with which we will have a better fuel efficiency. So that one way, and it will be having a cut fuel burn by 15%. There's a savings of 15% fuel efficiency being saved. So that's using GTF gear turbofan. And then lighter structures. So they have used some composites in our engines to reduce the weight. So once your weight is reduced, accordingly the fuel efficiency will increase. Next is aerodynamic upswept wingtips. So using the wingtips over here, their fuel efficiency also increases because they are reducing the drag accordingly. So basically, they have sharklets and uh, 737 blended winglets. So there are a lot of winglets, as you see here, the tips, which is used to reduce the drag. And lighter interiors and seats, fee for checked baggage, and these are taxiing from runway to one engine, special engine and aircraft washing programs. So these are the basic elements which is going to reduce our fuel. So accordingly, as you see, the price of crude oil has been increasing by year. So all the airlines want to have a better fuel efficiency. So these are some of the options as given for the airliners how to reduce fuel consumption. So as you see, the 787 is made of most of the carbon composites actually to reduce the weight. Okay. Coming to the engine noise. So engine noise is one of the major issue in fighter the engines manufacturing. So once the engine noise is higher, accordingly the fuel required, and there is a lot of discomfort for the passengers sitting inside. So when you reduce the noise, the thrust we can increase like anything. So there should be kind of like measures to reduce the noise. So how to reduce the noise is like they use a sandwich core in between that will actually help in the reduction of the noise. So with which we can have a multiple reflection of the noise, which will reduce accordingly when it comes out. Actually. So accordingly, we have to reflect the noise internally so that it should not come out at this point, which is using the sandwich, and there is a cowl which is made of it. So that's all like basic measures what they do for reducing the noise. Actually. Uh, so here you see the how the noises or limits have been restricted based on the every year of the number of airports. So these details which is giving here for each year how they are reducing the noise, the curfews, noise charges, noise level limits. So they are having a lot of restrictions in the airport also to have a reduction in noise during the airports. So it's a more important thing actually to reduce the noise. So basically they reduce the noise using a sandwich structure. So it's a basic design challenge. So the next is coming the driving factors for a commercial airport design. So what are the basically the demand for flights? How to be having so which maintenance cost should be very lower with that and more flying days. So the specific flight of the days, the maintenance cost, how much it is coming. That's the most worrying part from the airlines business. So they need the efficient engines to have a lower maintenance cost. So that's a basic expectation from any of the airlines. So demanding the technology advanced product, so very high competitive. And also like the specific fuel consumption. So they have to have consider the specific fuel consumption and reliable and easier to repair product. So they can have a easy repair condition. So after any the damage is going to happen to aircraft, they should have a easy to repair conditions. And also the checks, number of checks to be done in the inspections, quality inspection should be reduced suspect a period of time, and the product should have a longer life cycles. So these are the basic requirements from the airliners to have a better commercial aircraft uh, to to the operating cost for the flights. So next is like the driving factors for commercial aircraft reduced greenhouse. So how to reduce the pollution? So this is kind of like drive towards a cleaner and a greener aircraft engines and environment-friendly manufacturing and engineering technologies. So we should not have a higher fuel engine. So basically, how to have a better, greener airplanes is like increase the mass flow rate and reduce the thrust, dependent on the thrust, so that we will have lesser fuel injection with which the carbon which is going outside the nozzle will be reduced. So that's the basic idea to have a greener aircraft. Would be a kind of environmental friendly. So there is a chart actually how much is the green aircraft transportation. As you see, aircraft is only giving 9% of the pollution overall in the greenhouse gas emissions. So this is very less compared to your passenger cars, light cars. This because of like there are a lot of technology evolution happened in aircraft with respect to turbofan and mass flow rate increase and all these things. So, I just will be asking some interesting questions. So, you see any flights flying there, kind of like trails coming out like a smoke kind of thing. So, could you be able to identify what all these smokes coming from the trailing of the aircraft? Hello.
Yeah. Tell me.
So this trailing smokes, are you able to identify why it is coming? And I think you would have, many people would have noticed in the flights in the air which is going this kind of trails. Okay, I'll say something. This is a condensation trails. Okay, so why it is happening is because the hydrocarbon combustion, when your carbon dioxide mixes with uh, water droplets in the whenever there is a smog condition, there is a water droplets in the clouds, right? So when it mixes with this one, the condensation trails happens, and you see it will take some time to uh, make this one. So till here it is going to gap, and after that the condensation is going to happen. So this is how this one is happening. So this is basically condensation travels actually. It's because of dew drops mixing with the carbon dioxide in left out. So that's because of this condensation trails happening actually. Okay, so now coming to the just a second, 1 second. So hello.
Yeah. You can continue, Manish.
Yeah, so the cowling structure is surrounding the aircraft engine nacelle and thrust. I think this product, whatever being seen, it's cowl kind of cowl, and that's basically a nacelle and thrust rivers are physically interface with the aircraft engine and pylon. So there is a pylon which is attached to the flights, and there is kind of a cowl which is covering the engine. So this is one of the major aerostructure product which is covering the engine actually. So let's see what is the cover actually. The nacelle is a structure that provides aerodynamic sheath to the engine to provide a control engine and aircraft performance. So this is basically a cowl which has been covering the engines actually, and it is just guides a smooth airflow around the engines actually, and also the bypass flow is coming after the turbofan engines actually. And there are the different types of cowls. One is from inlet, which is starting, then the fan coil and thrust reverser at dislocation and exhaust. So that it's a kind of like uh, aerostructure product which is covering the engines. As you see, this inlet is a streamlined flow which is going, and you see here there's a small component. Why this is because it's like whenever there is a in the inlet there is a kind of like formation of ice systems is going to form. To condense the ice, they will just have a temperature of the thermal air which being traveling over here, which will condense the ice actually, and because of which there is a flow of ice in the vapor form coming out of the nacelles. So this because of the ice formation on the engine lip actually. So it's basically what all the components is there is fan coil doors, engines and latches, engine oil access door, and pressure relief and old open rods. So these are the old open rods. Whenever the maintenance is there, the fan coil be opened and the engine maintenance is being done. And also there is a kinds of hinges and latches. So that will just close. Hinge and latches will close a door actually. Uh, so these are the types of aerodynamic firing which is going to have major components actually. And coming to thrust reverser, so what is the purpose of thrust reverser is like the once it's been the flight is landed, it should have a lower runway to stop the flight. So they will just open up the thrust reverser with which uh, the bypass flow air will be reversed, and the thrust will not go this side, it will go to the opponent side, with which it just increase the drag so that it will stop at a very lower runway length. So that's the purpose of a thrust reverser in the engine cowl, to reduce the landing distance actually. And coming to the thrust reverser creates a reverse thrust by turning bypass air in the forward flow direction. As I said, that as you see, the engine bypass flow is going here, and once the thrust reverser is deployed, and there will be a blocker door which will block the air, and it will have a reverse thrust. So when it is being used, when you want to stop the flight during the landing position, so that's a time when it will be used for the thrust reverser is can deployed actually. And there are a lot of uh, the aerodynamic design which is required to have a better reverse thrust flow actually for this one. Okay, finally it comes to the exhaust. So exhaust is the portion which will have a bypass flow air, and you see the design is a kind of corrugated design. So the design is to have a aerodynamic smoothing wave, which is called chevrons actually. So aerodynamic smoothness is being measured so that engine mass flow rate, which is going here outside here, should have a lesser drag to have a better aesthetic design. So to meet that, they have a chevrons actually, which has been designed in the nacelle product. And coming to the engine mounts, what is engine mounts? So the engine is being mounted over a pylon, or from pylon to the wing. So this is the actual link rod which is holding the engine. Which will, if you don't have this link rod, I think the engine will drop down. So it will just holding, and from here the pylon structure is going to the structure which is going to the fixed. The whole engine is fixed on the pylon structures. So this is a kind of a very primary structure, and it's designed under fail-safe and damage tolerance design. So the design of this one is a very critical design, and there are a lot of design caution thing is going to be taken care while designing this pylons and the engine mounts. So then the engine build unit. So what is the engine build unit actually? It's basically the fuel lines, cable lines, fuel lines, which is going on here, and there are a lot of fuel lines as well as the uh, electrical installations, cables, lines, which is all going. So all these designs are being controlled by engine build unit actually, and there are a lot of systems where we have pneumatic system, fuel systems, electrical systems, power generation, and design criteria. So basically, the design criteria covers with respect to heat resistant materials, and the pressure proof and burst requirements, and the vibrations is checked for it, and the core engine vibration levels is also being checked for all these installations. So even a small failure is going to happen. The fuels or the electrical lines is going to leak out, I think it would be a big trouble for whole engine design. So it has to be checked, and it has to be tested and designed accordingly so that it should have a no leakage proof actually. So these all like very critical installations which to be taken care of in your design as well as your installation and assembly level. Okay, so there is a kind of APU, auxiliary power unit, over here at the back end of the flight. So when it has been used is when your engines are not functioning at your flight condition. So they should have an alternate option of engine. So that time this auxiliary power unit has been on, so that if your engines are failed and it's not functioning during the time the auxiliary power unit is being used to have enough extra thrust actually. So this is only during the emergency condition they will on, and it will not be on for all the times actually. Whenever your flight engines are not functioning, that time they use the alternate power, which is nothing but your auxiliary power unit, which is placed in the end of the flight section. And there's also a simple engine mechanism which has inlet and a lot of compressor plates over here actually. So this is the function of auxiliary power unit which is used actually. And some of the new technologies we've been mentioned. So what are the basic engines we use? GENX 10000, AF350 XWB, and gear turbofan as we use. These are the small engines which is used. Gear turbofan used in Bombardier A320neo flights actually. And this side, if you see, this is a Trent engine and G engine which is used for the larger aircrafts, and this for smaller engines actually. So these are the basic engines which is used in most of the commercial flights used actually. So coming to the next flow, this is a kind of how the commercial flight is being used, port and starboard. So when you have a left-hand side, we will be calling as port, and this is a common terminology used in the flight systems when doing your maintenance. So they, for left-hand side, they used to call as port, and the right-hand side is called as starboard actually. Uh, so you see, it's like the cargo. So where is the cargo is loaded in the flight systems is kind of at the starboard side. So that is at the RHS side. So there, that cargo, like your passenger, the luggages is used to mount over in the cargo. Yeah. So coming to the next slide. So this is a one of the commercial aircraft which uses the very delta wing concept. But it's actually a failure. But it is being designed by UK to have a Mach number 2. So it's a delta wing concept. It's a droop nose. The nose will be shortened here actually, and it has afterburner also. But this fighter aircraft, this is a commercial aircraft. They designed with respect to Mach 2, but later on it has a lot of stability issues, so it has been cancelled. But they have tried for a new innovation with the delta wing concept for commercial flights. That's all I think. So if there are any questions from your side.
Any doubts and any questions from student and the faculty sides? So do you have any questions? Please ask me, Mr. Manoj Kumar sir. Any questions related to the aircraft and as well as the related to the propulsion system? So please ask him. So any doubts, please ask them, students as well as faculty members. Sir, Dindan sir. Can you give me?
Yeah. Am I audible?
Yeah, audible, sir.
Thank you very much, Mr. Manoj Kumar Sabhanayagam, for the wonderful presentation on the titled Design Principles of Air Breathing Engines and Nozzles. Normally, flight journey, everyone will like to travel. That if you travel by business class, it will be a very wonderful experience. Similarly, you have covered all the topics like types of aircraft, engines, and their applications, aircraft engines and efficiencies, driving factors for commercial aircraft design, nacelle and thrust reversers, and ASC programs and new technologies. So it's really very wonderful experience for all of us. The students as well as faculty, really they have enjoyed your wonderful lecture. That to Saturday evening, you have spared your valuable time and given a very wonderful lecture on the aircraft. Thank you very much, Mr. Manoj Kumar. Thank you. And I would like to thank the faculty members as well as students for attending this program. Thank you very much.
Thank you, sir.
Thanks.
So, any doubts, students and faculty members?
So actually, you can ask any questions. So because I worked in most of the components, actually. All the components I have covered actually. Engines I have worked, and I have worked on natural, and the full engines I have designed it for the Boeing actually. Like, you can ask any questions because maybe as an industrialist, I know each and every part of the engine.
Okay, thank you, sir. Thank you, Mr. Manoj Kumar, sir.
Thanks.
For accepting our request and as also giving for very good lectures and lessons. So thank you once again, Mr. Manoj Kumar, sir.
Yeah.
Sir,
Thank you.
Chinnan, sir.
Thank you, pa. Okay.
Wind up பண்ணிக்கலாமா சார்?
Wind up பண்ணிக்கலாம்ப்பா.
Okay. Thank you.
I think now I sent the presentation to Ramesh also. If you want, you can take the presentation to for your reference, future reference.
Okay, sir.
Okay then.
Okay, thank you. Thank you all of you.